Welcome to this video introduction to TensorFlow. Imagine we have an image like this one. We want to identify what is in the image, in this case, a cat. The image is the input, and cat is the desired target. The question is, how do we get from input to target? We use a series of mathematical functions and operations, which form a computational graph, to transform the input into the target output. This method must work not only for this one cat image, but for other cat images as well. This process is part of a field of machine learning known as deep learning. So what exactly is TensorFlow? It is an open-source library for deep learning, developed by the Google Brain team and released in November 2015. Now let's look at how to install TensorFlow. For Linux and macOS, the installation involves downloading Anaconda, creating a TensorFlow environment, and using --conda and --pip commands to install the necessary libraries and TensorFlow itself. For Windows, the steps are similar. Download Anaconda, create the environment, and use --conda and --pip to install the libraries in TensorFlow. Next, we will cover some fundamental concepts of TensorFlow. The goal is to go from an input image to the output classification cat. This transformation is done through a model. If the model predicts non-cat, while the actual target is cat, there is an error. This illustrates the input prediction target flow. The input image leads to a prediction from the model, which is compared to the actual target. The difference between the prediction and the target is measured by a cost function. The output of the cost function is the error, which indicates how far off the prediction is from the target. This error is then fed back to an optimizer, which adjusts the model to reduce the cost in subsequent predictions. All these components, the model, cost, and optimizer, are defined within a computational graph in TensorFlow. The graph outlines the flow of operations from input to output, including the model, cost function, and optimizer. The graph structure also includes placeholders for inputs and targets. Placeholders are gates, for example, input. The model makes predictions, the cost function computes the error, and the optimizer minimizes the cost. A session brings the graph to life by injecting real data, consisting of inputs and targets. The graph is the layout of the process without data. Data consists of inputs and targets. The session is where the graph is executed with data. If the input is cat, the target is cat. The model currently predicts non-cat, causing the cost function to measure the error. Let's say the calculated cost is 100, indicating a large error. The optimizer adjusts the model's variables, this is the training step, to decrease the cost. After training, the model predicts cat with the input cat, and the cost is now close to 0. Let's look at a simple hello world example. We will implement the sum of two integers using TensorFlow, starting with importing the library. The goal is to calculate the sum of two numbers. We define the graph with placeholders for our numbers a and b, and the operation tf.add. Then, we define the input data. In the session, we run the graph using _ses.run, feeding the data via _feed_dict to the placeholders. The outcome will be the sum of the two integers. Next, we will explore regression in TensorFlow. Our mission is to train a model to learn how to perform addition based on 10,000 examples where x1 plus x2 equals y. Instead of knowing the operation is addition, the model must learn the correct operator represented by the question mark. For example, the model sees inputs 7 and 6 resulting in target 13, and so on for 10,000 examples. We assume the relationship between the inputs, x1 and x2, and the output, y, is a linear function of the form x times w plus b equals y. In this linear equation, w and b are the variables that the model needs to learn during training. Now let's relate this to a neural network structure. The linear relationship is expressed as x times w1 plus b1 equals y. The network takes the inputs, x, and applies the weights w1 and bias b1 to produce the output y.